so we're going to get started with gas stoichiometry. Gas stoichiometry is no different than any of the other stoichiometry we've been doing, but it's just going to be how do we get to moles. So the question, remember, for any type of stoichiometry is how do we get to moles? And then once we get to moles, we can do anything. So now that we have the ability, because we have PV equals nRT, and we have a mole component, we can find moles, so we can do stoichiometry with gases. So this is a reaction that's used in airbags. So the reaction that's used in the deployment of automobile airbags is the high temperature decomposition of sodium azide. So this is sodium azide to produce nitrogen gas. How many liters? So how many liters of nitrogen at 1.15 atmospheres and 30 degrees Celsius are produced by the decomposition of 45 grams of sodium azide? So this is the information. We still need to put the 1.15 and the 30 in there. So first thing we need to do is we're going to find moles of sodium, we're going to find moles of sodium azide and convert that to moles of nitrogen, because we want to know how many liters of gas that's going to make. And so we need to be talking about nitrogen, because we're saying that the nitrogen has the 1.15 atmospheres and 30 degrees Celsius. Okay, so 30 degrees Celsius, we have to add 273 to that. So we add 273 and we get 303. Okay, so let's start. So we have our information here. We need 45.0 grams of sodium azide. We want to know how many grams per mole. So we're going to look at the periodic table. We're going to add it up and find out that that's 65 grams. So nothing different here. We've done this a ton, right? Just using molar mass to convert to moles of sodium azide. So grams cancel. We're now in moles. Once we have moles of sodium azide, because this is a balanced chemical equation, we can go to moles of nitrogen. So for every 2 moles of sodium azide that decompose, we're going to get 3 moles of nitrogen. So that's our moles of nitrogen. We calculate that. So 45 divided by 65, 45 divided by 65 times 3 divided by 2 gives us 1.038461538. And 3 significant figures would be 1.04 moles of nitrogen. And while we don't try to round to the end, it's okay. I'm just going to round it here so we can put it into the next equation simply on the page. Now we have PV equals nRT, right? PV equals nRT. We want to know volume, so we're going to divide both sides by P, and we get V is equal to nRT over P. So volume is equal to, so number of moles we just calculated, 1.04 moles of nitrogen, times R, which is 0.0821 liters times atmosphere over mole times Kelvin. All right, then T, which is 303, 273, just double check, plus 30 is 303 Kelvin, divided by the pressure. The pressure is 1.15 atmospheres. Cancel our units, moles cancel, Kelvin cancels, atmospheres cancel, and we do the math. 1.04 times 0.0821 times 303 divided by 1.15, and we get 22.49682783. So that would be 22.5 liters of nitrogen. So really, the first part is just how do we get to moles? Just like always, we can do any stoichiometry we want with this, just got to get to moles. So that's how we do that. Well, this is simple to go to moles, just using molar mass. So that part probably wasn't the hard part. It's just the how do we find what we're looking for later. So we need to be able to put all these things that we've learned throughout the year together in this sense in order to get where we're going. All right, let's try another one. So let's take a look here. Sodium peroxide is used to remove carbon dioxide and add oxygen to the air supply in spacecrafts. It works by reacting with CO2 in the air to produce sodium carbonate and oxygen, so it's called a scrubber. What is the mass in grams of Na2O2? So what is the mass in grams required to consume 2 liters of CO2 at STP? So we have to remember what STP is. So try it, pause it, try it, and see what we need to do here. So we're going to start with PV equals nRT. So the pressure is going to be 1 atmosphere. The temperature is going to be 273 Kelvin, because that's STP. The volume is 2 liters. The number of moles is what we're looking for, because then we're going to take these moles and convert to moles of that, and then to grams. And R is 0.0821 liters times atmospheres over mole times Kelvin. So we're going to be solving for N. PV equals nRT. So PV divided by RT equals N. Do that over here. So N equals P times V over R times T. So the moles then are going to be, so 1 times 2 divided by 0.0821 divided by 273 is 0.0892327324. And it just brought up a point that when I'm talking about this and I say 1 times 2 divided by 0.0821 divided by 273, when I put this in my calculator, I'll put 1 times 2, then I'll hit the division sign, divide by 0.0821, and I hit equals. And then I hit divide by 273. You can also say divide by the quantity 0.0821 times 273, but you need to use brackets. So if you're not getting the same answer as me, contact me. We can always video chat and I can show you what I'm doing. We can figure it out, okay? This is moles of CO2. We need to now convert that to moles of Na2O2 and then to grams of Na2O2. So start there. We can round it if we want. 0.0892 moles of CO2 for every 2 moles of CO2. We get 2 moles, we need 2 moles of Na2O2. There we go. And 1 mole of Na2O2 has a mass of, let's see, 22.99 for sodium times 2 plus 32 for the oxygen is 77.98 grams of Na2O2. So putting it all together, 0.0892 times 2 divided by 2 times 77.98 gives us 6.955816 grams. 3 significant figures would be 6.96 grams of Na2O2. So that is gas stoichiometry. We are going to move on to Dalton's law. Dalton's law would be the one that you're going to be using for the gas laws lab. So there's a couple different ways to apply Dalton's law. So we'll see that in just a minute. Dalton's law is called Dalton's law of partial pressure when we talk about a mixture of gases. So you come into contact with mixtures of gases probably far more than you even realize, because air alone is a mixture of gases. So breathing air, I used to fill breathing air when I worked at Airgas. Breathing air is a mixture of 21% oxygen, balanced nitrogen. So whatever we don't have for the 21%, so if we're like 20.99, the rest of it would be nitrogen. Now, typical air that you breathe from a building or whatever is around you in your home is pretty much this, but it has a small percentage of argon, less than 1%. And there are some impurities in there as well. But when we fill breathing air, we also have to put moisture, make sure there's enough moisture in there, because if we don't breathe in, we'll dry out everything in our sinuses and everything. We'll breathe it out, it'll dry it all out. So you'll notice if you have a CPAP or you know somebody with a CPAP, there's always moisture involved in that. And there's also, if you dive or anything like that, there's going to be moisture in those tanks to make sure that you're not drying out your air passages. as you're breathing in this air. So this is important that we have this mixture of gases and we have it the same whenever possible. So if you go diving, I dive, I don't know if you guys do, but diving is really fun, but you have to make sure you have the right mixture of air, the right amount of moisture, and that you're not diving too long. So since this has nitrogen in it, we have to be very careful when we're diving. When we come back up, we can get something called the bends if we come up too fast, where you have the nitrogen in your bloodstream actually expands and the bubbles can kill you. So that's called the bends. But actually, we do heliox mixtures, so helium and oxygen mixtures for deep sea diving. So this would be like somebody maybe in the Navy, like a Navy SEAL, or somebody that's got to go plus 300 feet down into a place. This would be a heliox mixture where we're mixing with helium instead, so that they don't end up with as severe of problems from diving for longer or diving deeper. So mixtures of air are important. If you've ever heard of somebody climbing Mount Everest, they have to take safety stops. So safety stops. And they probably said, well, the air is thinner. The air is thinner up there. Well, sort of. Okay, so total pressure, and if we're talking about the total pressure around us right now that we're used to is about 1 atmosphere. And we said 21% of that is oxygen. And that's what we're used to. So pressure, the partial pressure of oxygen is about 21% of that. And then we have the partial pressure of nitrogen that is going to be adding together to equal 1 atmosphere. Well, the air isn't necessarily thinner, it's not as high of a pressure. So as you go up the mountain and you're climbing up the mountain, the pressure gets less. So there's less pressure. I think I just drew that the wrong way. So I'm just going to write less pressure because I want to think about it right now. Less pressure. So there's less total pressure here. So the percentage, even if it were to remain the same, would not be the same number, would not be the same what your body is used to as far as partial pressure is concerned. Your body, however, is what we call plastic. Yes, not talking plastic surgery kind of plastic. We have what's called plasticity. And that means your body is able to adapt to its surroundings. So if you are climbing and you wait here long enough, your body will adapt to that certain amount of oxygen. Now there are Sherpas and people that live in the mountains and near Nepal that they can just run right up the mountain because they're so used to living in there. They still have to stop every once in a while, but they don't have to stop nearly as often as a Westerner that were to come over because they're used to living at a less pressure of oxygen to begin with. So these safety stops are so you don't pass out. If you have lung problems or heart problems, you shouldn't be climbing the mountain, but also you can take oxygen tanks, and you should take oxygen tanks just in case you start to feel lightheaded. It can become a problem. So it's not really that the air is thinner or there's less oxygen because there's less oxygen. It's less oxygen because there's less total pressure to keep that. So if you go up really, really high and you climb, the pressure becomes less. If you dive down really, really low, the pressure becomes high. You're under the water, it'll crush you like a tin can. So under the sea, really high pressure. Up in the air, up in a mountain, is very low pressure. One of the big things that if you can understand this and you can get this, we can really do a lot with what are called mole fractions. So mole fractions can be kind of confusing at first because they relate a bunch of different things, but let's take a look at them and try to figure them out. So a mole fraction, it just compares the relative amounts of moles in a gas mixture. And we can use this mole fraction because it ends up being unitless to compare pressure as well. So the number of moles of a certain component in the mixture divided by the total number of moles gives us what's called the mole fraction. So this is the mole fraction. And it's Xi. So if we were talking about oxygen, it'd be NO2, this would be XO2. So that I is just depending on what we're interested in. So over the total number. So this is just telling us basically how big of a portion this gas makes up. And they're going to be proportional. So the number of moles and the pressure are going to be proportional at specific temperature and volume. So if we keep the temperature and volume the same, the pressure is going to be proportional to the number of moles. So look at the same Xi, if we did O2 here, O2 would be the same. So we could actually say, well, if I know the mole fraction, I can figure out what the partial pressure is, if I know the total pressure. Or if I know, these components here, I can figure out what the number of moles are. So I can go back and forth between them. Now note, mole fractions are always less than 1. The sum of all of the mole fractions should equal 1 within a few hundredths or something like that if we had significant figure issues. And mole fractions are always dimensionless. So moles divided by moles is 1, right? And whatever ATMs or whatever pressure unit you're using, they're going to cancel out because whatever it is divided by itself is going to be equal to 1, so it cancels out. A gas cylinder contains a mixture of nitrogen and helium with partial pressures of 35 atmospheres, nitrogen, oxygen, and helium, with partial pressures of 35 atmospheres of oxygen, 5 atmospheres of nitrogen, and 25 atmospheres of helium. What is the total pressure inside the cylinder? This is probably the most simplistic version of Dalton's law that we can have. The total pressure is equal to the partial pressure. In this case, there's 3 gases of oxygen plus the partial pressure of nitrogen plus the partial pressure of helium. So we just add up all of the different gases are there and it'll give us the total pressure. So 35 atmospheres plus 5 atmospheres plus 25 atmospheres. So 40, 50, 65. So 65 atmospheres is our total pressure. And again, probably the most simplistic version of Dalton's law that we can put together. A container with 2 gases, helium and argon, is 30% by volume helium. Calculate the partial pressure of helium and argon if the total pressure inside the container is 4 atmospheres. So a percentage is actually another way of saying that it's going to be like a mole fraction, right? Because it's a fraction out of 100. So if I take 30% and I convert that to a decimal by dividing by 100, I get 0.300. That's essentially our mole fraction. So we know that it's 0.300 is equal to, we're looking for the partial pressure, is looking for the partial pressure of helium, so PHE, over the total pressure, which is 4 atmospheres. So we'll just take 4 atmospheres times 0.300, and that will give us the partial pressure of helium. So 0.3 times 4 gives us 1.2 atmospheres, and it would end up being 1.20 of helium. Now, how do we figure out that of argon? Well, there's a couple different ways. We know that the total pressure is 4, that's PT, and we know the partial pressure of helium is 1.20, so the partial pressure of helium. And we know that we have to add the partial pressure of argon, get ahead of myself here. So we could just solve for that, or we could also say that if it's 30% helium, it must be 70% argon because there's only 2 gases in the cylinder. I'm probably just going to subtract because it's easier, right? So that would be, the partial pressure of argon would be 2.80 atmospheres of argon. A mixture of 14 grams of hydrogen, 84 grams of nitrogen, and 2 moles of oxygen are placed in a flask. When the partial pressure of the oxygen is 78 millimeters of mercury, what is the total pressure in the flask? This is probably a more difficult version. So we know that the total pressure in the flask is going to be equal to the partial pressure of hydrogen plus the partial pressure of nitrogen plus the partial pressure of oxygen. We are given grams, grams, and moles. We're given enough information to find moles of all components. So we can probably find a mole fraction. So let's take a look. So the mole fraction, so 14 grams of hydrogen. Hydrogen has a mass of 2.016, right? 1.008 times 2. It's 2.016 grams of hydrogen for 1 mole. So 14 divided by 2.016 is 6.94 moles. Nitrogen, 84 grams of nitrogen. There's 28.02 grams of nitrogen for 1 mole. So 84 divided by 28.02 is 2.998. We're going to keep that extra one so I don't have to round right now. All right, and then we have moles of oxygen. We were given as 2.00 moles. So I can add these up and get N total. So 6.94 plus 2.998 plus 2 is 11.938 moles total. All right, now where do I go? I want to know the total pressure in the flask. So I want to know P total. I'm given the partial pressure of oxygen. So if I know the mole fraction of oxygen, excuse me, I just wrote that wrong. I meant to write that on the bottom. So I want to know P total. If I know the partial pressure of oxygen and I know the mole fraction, I can find, because if I know this and I know this, I can find this. So let's get the partial pressure of oxygen. So this is going to be Xi, or XO2, is going to be 2 moles divided by the total. So 2 divided by 11.938 is 0.1675. And remember, this is unitless. So that gets put in place of the Xi, or the XO2 in this case, is going to be 0.1675. It's unitless. On the top here, the partial pressure of oxygen was given as 78.00 millimeters of mercury, and we're going to solve for P total. So P total, I'm going to erase this part here. Running out of space. So P total is equal to 78 millimeters of mercury divided by 0.1675. So this would be 465.582 millimeters of mercury. Or 466 millimeters of mercury is P total. So that's about as hard as it gets. We can see that there's some confusing things we need to maybe look into, where we have to apply a bunch of different concepts that we learned here in order to make this work. So sometimes there's some work involved. So why is this important? I like to bring up this example because not everybody that works with you, or depending on what you do for a job, is going to have a degree in chemistry or have ever taken chemistry. Not everybody is going to be looking out for your safety, so you need to be looking out for your safety all the time. So most of the large steel-sized 300 gas cylinders are rated to hold a maximum of 2200 psi. If they're stamped with a plus sign, they can be filled to plus 10%. So if the filler, we'll call him Tony, is talking to his friend and forgets what he's doing, and he fills the cylinder with 250 psi of oxygen, 500 psi of argon, and 1775 psi of nitrogen, is the cylinder safe to ship? So this is going to be somebody's job to be just shipping these cylinders, labeling them, make sure all labeling is right, but they're not going to be checking the pressure of the cylinder. So that's the filler's job. And the filler may never have taken a safety course or never have paid attention during the safety course, because the same guy named Tony may also be smoking a cigarette while he's filling the flammables, but we'll just consider that another day's topic. So you figure out, this is your job, is it safe to ship? Pause it and try it. All right, hopefully you came up with no, because the total pressure inside the cylinder is 2525. And if we have 2200 plus 10%, well, what's 10% of 2200? Is 220. So it'd be 2,220. There we go. Plus 2020, right? Gives us 2420 psi. And this is 2525. Uh-oh. So what happens? You know, you've all seen it on TV, right? The valve shears off and it goes through a wall. No. So don't be afraid. This is what's supposed to happen with a cylinder. You'll see a seam down the side. They're supposed to open like a clam and release the gas. There's also safety valves in the valve itself that should release prior to the cylinder exploding. But you should always do your due diligence and pay attention at work to what you're doing, because if this doesn't explode now, it could explode in transport, it could explode at the location, and it could hurt someone. So just because it's not going to shear off the valve and run through a wall all the time doesn't mean it's not dangerous. When these valves go off, it sounds like somebody is standing next to you just screaming really loud in your ear. They get very cold because they're releasing the gas really quickly, and it is loud. If the total pressure of a mixture of gases is 290 atmospheres, so P total is equal to 290 atmospheres, the mixture contains 122 atmospheres of nitrogen and 76 atmospheres of hydrogen. What is the partial pressure of helium? So we have nitrogen, we have hydrogen, and we have the total pressure. So nitrogen is 122 atmospheres, and hydrogen is 76 atmospheres. So we're going to say 290 atmospheres minus 122 atmospheres minus 76 atmospheres. And we get whatever 290 minus 122 minus 76 is, which is 92, is the partial pressure of helium. So some of them can be very simple as well. So many times we'll use Dalton's law in an even a more expanded way. So what we would have done in lab would have been an expansion of Dalton's law where we collect a gas over water. So when we do that, we have to take into account not only the gas pressure, but also the water vapor. So we're going to take a look at a couple of these, and hopefully it'll help you with your lab. A 250 milliliter sample of oxygen is collected over water at 25 degrees Celsius and 760 millimeters of mercury. What is the pressure of the dry gas alone? So we have the temperature, which is important because the temperature is going to tell us what the water vapor is at that, because water vapor is going to be the gaseous water. That's going to be adding pressure that we need to subtract in order to get the pressure of just the dry gas, in this case oxygen. So you'll notice in your lab there were some equations. So one said P gas is equal to pressure of the atmosphere minus pressure of the water. And so for this one, we need to have the pressure of the atmosphere. So we would have the atmospheric pressure. In this case, it's given. So 760.0 millimeters of mercury. And then the pressure of the water. So in order to get the pressure of the water for lab, there's a table in your lab that tells you. So depending on what the temperature is, you'll get the pressure. So at 25 degrees Celsius, which is what this experiment was done under, 23.8 millimeters of mercury are going to come from just the water vapor. So then we do a subtraction problem and we get 736.2 millimeters of mercury. And then we round that to three significant figures. Actually, no, this is just a subtraction problem. So we just go to the number of decimal places. So the number of decimal places is actually going to be 1. So 736.2 millimeters of mercury would be our final answer. So that is the pressure, and we should say, of oxygen. So I'm going to erase that so I can put oxygen in there because we need to have a number, a unit, and a label, Mrs. DeVos, right? Okay. Number, unit, label. Good. All right. We're going to skip ahead to the next one. A 32 milliliter sample of hydrogen is collected over water. So over water tells me I have to get rid of the water vapor in order to get the pressure of the dry gas. All right, so it's collected over water at 20 degrees Celsius and 750 millimeters of mercury. What is the volume of the dry gas sample? So before we were asking about the pressure, now we're going to ask about the volume. So we can assume the number of moles is going to be kept the same, so we can use the combined gas law. P1 V1 T2 is equal to P2 V2 T1. So in this case, we're going to solve this for our volume in the second one, because that's what we're looking for. So we need to make sure we have all of these variables. Well, this is at STP. So at STP, which means we're going to have P2 and we're going to have the variables for that. Well, can't talk sometimes. So at STP means our P2 and our T2 are going to be our STP values. So we have those. P1, V1, and T1 are all given to us. So we'll convert this to liters. Actually, we don't need to convert it to liters because we can just answer in milliliters as long as they're the same. We're not using R. Since we're not using R, we don't have to convert. We will convert this to Kelvin, and this will be our T1. And this is our P1 right here. So we have those variables, but first we need to get what is the pressure, because this isn't really P1, right? We need to subtract the water vapor. So let's get our pressure of the gas itself. So we're going to take pressure of the gas minus the pressure of the atmosphere minus the pressure of the water. All right, so the pressure of the gas, in order to get the pressure of the gas, we take the 750 millimeters of mercury, and that should have a decimal place, and that'll be important in a minute, I guess. So I better put it in there. We're going to subtract from that the pressure of the water, which is 17.5 millimeters of mercury. This was given right here. So when we do that, we should get 732.5 millimeters of mercury. So this is our pressure of the gas. The gas is hydrogen. So this is the pressure of our hydrogen. Well, that's not our final answer. We want to know the volume of the hydrogen under STP conditions. So this is something similar to what you had to do in lab. So first, you're going to look for your variables. So P1, V1, T1, P2, V2, T2. I have not changed the number of moles, so I do not have to use PV equals nRT. I can just use my combined gas law. So pressure number one is this one that we found. So pressure number one is the 732.5 millimeters of mercury. We're saying under these set of conditions, this is what we got. 20 degrees Celsius, the temperature, so 20 degrees Celsius plus 273 equals 293 Kelvin. The volume was 32.0 milliliters. So we're saying this is what we collected under these conditions. What would we have collected, or what is that same volume under this second set of conditions? So instead of being at 293 Kelvin, we're going to be at 273 Kelvin, and the pressure, instead of being 732.5, would be 760 millimeters of mercury. So we're just changing the conditions and seeing how the volume is going to react. So V2 is equal to P1 V1 T2 divided by P2 T1. So we plug in those values. P1, 732.5 millimeters of mercury. Might run out of space here. V1, 32.5 milliliters. And T2, which is 273 Kelvin. We divide by P2, which is 760. and T1, which was 293 Kelvin. And when we do that, we should get 28.73684,211. And our sig figs should be 3. Our volume is 3. So 28.7 milliliters of hydrogen gas. So I think the most confusing part about this is trying to figure out what we do here and why we need to do that. So why do we need to do that? Because we collected the hydrogen over water, some of that water vapor was mixed in with the hydrogen gas, and we would like to know what the sample of gas of just purely hydrogen was. So we need to subtract that to get just the pressure of hydrogen. Once we got the pressure of hydrogen, we're actually asking about it at STP now. So then we're just doing a regular combined gas law problem. So hopefully that helps you with your lab, and we're going to move on. The kinetic molecular theory. Now we mentioned a few of these things in the beginning, but I just want to make sure we have a slide where we're talking just about the kinetic molecular theory and the assumptions that we make. So the kinetic molecular theory tells us that a gas consists of tiny particles. Those particles could be atoms, they could be molecules. So atoms would be something like xenon or any of our noble gases, neon, like something like that, where they're just single atoms. Molecules, that would be like our hydrogen or nitrogen, anything like that, CO2, where we have more than one particle, or excuse me, more than one atom. And they are moving about at random. So they're constantly moving in random ways. They're going to run into each other too. The volume of the particles themselves is negligible because they are so small, and the space between them is so vast. So this is where we're talking about the difference between water, liquid water taking up half a golf ball, and gaseous water taking up more than 3 volumes of basketballs. So compared with the total volume of the gas, the particles themselves are considered negligible. So most of the gas is actually empty space. The gas particles act independently of one another. They feel like they have no neighbors. So there's no attractive or repulsive forces. Remember, these are assumptions. These are assumptions we are making. Collisions of the gas particles with other particles or with the walls of the container are elastic. And elastic collisions means there's no energy lost or gained. They are going to be perfectly elastic. They're going to transfer just as much energy as they receive, and they won't slow down. So that's at constant temperature. The average kinetic energy of the particles is proportional to the Kelvin temperature of the particles. So we talked about this, it must be in Kelvin, and we talked about, how the kinetic energy is equal to 1/2 the mass times the velocity squared, and that we can relate a lot of different particle motions to this, because if we're changing the temperature, we're going to be changing the speed of the particles. So the average speed of gases, if you look here, hydrogen is going an average of 1,960 meters per second, versus CO2 is only going 415 meters per second. So why is hydrogen so much faster than carbon dioxide? And honestly, it's based on their mass. So if you look at the mass, as the mass increases, the speed decreases. So as the mass, the molar mass, increases, the speed decreases. So it's just going to be harder to move something that's heavier. That's all. So you can look at two gases and you can say, well, I know oxygen is going to move slower than hydrogen because oxygen has way more mass. So that's how we do that. Now we have some different terms we're going to look at here based on Graham's law of effusion. It used to be known as Graham's law of diffusion. So what are the difference between those two terms? Effusion is the escape of gas particles through just a pinhole into a vacuum without molecular collisions. So there are no molecular collisions taken into a point. Where diffusion is where we're mixing gas molecules by random, and the random motion is going to just randomly mix them together. So we're not a pinhole, there's no vacuum, and this is just under regular conditions where molecular collisions are occurring. So they're going to be bouncing off themselves, they're going to be bouncing off the walls. That's normal. So this is when I talked about opening a bottle of perfume, I was talking about diffusion versus effusion is a little different. So Graham's law tells us that the rate of effusion is going to be inversely proportional to the square root of the mass of its particles. So this is just the mass of the particles, and we can figure out that what is the rate. So we can do that. We can compare rates of other gases as they go through. And the last thing I want to talk about is what is the difference between a real gas and an ideal gas. We've been talking about the ideal gas law. So what is an ideal gas? And I kind of mentioned this as we went through, that every gas is a real gas, and there is no such thing as an ideal gas. An ideal gas is something that follows all the assumptions of the kinetic molecular theory. The kinetic molecular theory is a theory. It is something that is making a bunch of assumptions. And the ideal gas law, even though there is no such thing as an ideal gas, is going to be an excellent way to estimate the behavior, the physical behavior of a gas at or around standard temperature and pressure. So at or around standard temperature and pressure, real gases behave like ideal gases. It's when we deviate largely from STP that we see the behavior change. And if we think really hard about this, it actually makes a lot of sense why these would start to deviate from the ideal gas behavior. So if we look at the assumptions of the kinetic molecular theory, they have no neighbors. They feel no neighbors. So if we look at where do real gases deviate most from ideal behavior, very low temperatures. Okay, Ke is equal to 1/2 mass times velocity squared. We said that particles are moving really fast. They're bouncing off one another. If we lower this energy so much that this velocity, the speed of the particles, goes down that much, the particles are going to start moving very slowly, and they might actually stick together. So they don't have enough energy to overcome moving away from one another. So the attractive forces become so strong they can't resist. Also very high pressures. So if I've got a gas here and I've got all these particles randomly moving around and they're not, they don't notice each other or anything like that, well, then I decrease. I take a piston and I just push it down here. And I have this container, but now all the gas particles are trapped in way less space and they're right next to each other. They're no longer going to have the space to take up that they would have had, so they're not going to be able to ignore the attractive forces that are holding them together. So if we go back here to the kinetic molecular theory slide, we said there are no attractive or repulsive forces. If we increase the pressure high enough, they can no longer ignore those attractive forces. There's now going to be anywhere for them to go. So we're taking away that space that allows them to not feel the attractive forces of their neighbors. But if we take away too much of that space, they're going to start attracting one another. So the volume of a real gas is actually larger than that predicted by the gas law for real gases, and attractive forces between particles actually become more important at higher pressures. So this is what we were just talking about. So at low pressures, the volume of gas particles is actually negligible. We talked about that. We don't look at the individual gas particles, but since here we're putting a lot of pressure on here, moving this piston down, and now the volume of the gas particles is way more significant, because if they're larger gases that take up a lot more space, they're not going to have any room. So that total volume is going to matter, and it's going to have to be taken into account. So if we're at or around standard temperature and pressure, we can ignore these forces. So those are called, and if you remember, van der Waals forces. Those are the intermolecular forces that we were talking about in the previous chapter. So these are the van der Waals equations, and this corrects intermolecular attractions. This R is supposed to be up here. So this corrects intermolecular attractions, and this corrects for molecular volume. But I don't know about you, this is our perv-nerd equation with those in there. I prefer PV equals nRT whenever possible. So as long as we are at or around standard temperature and pressure. So when does it deviate most? Most from ideal behavior? High pressure, we're pushing them close together, and low temperatures, when they start to get really close together because they're cold and they can't move as fast. That says temperature. I think there should be another T in there. There you go, temperature. Well, that's it for gas laws. I hope you enjoyed it. I love gas laws. We have one more chapter to do, and then we're done with lecture. Oh my goodness, it's getting close.